Today we're going to do the Test 1 review for Physics 2010. Logistically, this is going to be held in person. I really hate online testing. I'm not going to do it unless they make me, okay? So, test in person on Thursday, September 16th. If you can't make the test in person, we'll have to schedule a makeup, okay? And you need to email me to contact me about that. Remember that I have to grade this, so I need to be able to read it. So please do write legibly and make sure that when you do your problem, you have it ordered on the page in a linear, logical fashion that's easy for somebody that can't read your mind to follow it. Now, you don't have to show every step of your math, but bear in mind, if you show more work, I can give more partial credit if you make a mistake. But at a very minimum, you need to tell me what equation that you're using and show me what numbers you're putting into the equation for each variable, okay? Don't forget your units. If you don't show at least that much work, then I'm going to deduct points because I'm not going to know what you're talking about. If you don't have the right units or the right notation, I'm going to deduct points. You are going to be graded on notation. We're going to cover material in chapters 1 through 3 in matter and interactions, but we're not going to be tested on computational or VPython skills on this test. It's just an analytical test. You can bring an index card that's 3 inches by 5 inches to the test as an equation sheet. Also bring a calculator, a scientific calculator. So bring scientific calculator. I'm not going to let you use your cell phone or a laptop or a tablet to do calculations. And you might want to bring some scratch paper, okay? So bring blank paper. Now, I'm going to give you any of the fundamental constants that you need, like the gravitational constant, big G or little g or epsilon naught, things like that, so you don't have to waste your note card space on fundamental constants. But one thing I'm not going to tell you is the SI powers of 10 prefixes. I really want you to memorize those, okay? Now, you don't have to memorize all of these. This table shows all of them from yotta to yocto. I just expect you to know from giga to nano. So from 10 to the 9th to 10 to the minus 9, and it's mostly in steps of 3 orders of magnitude, so that shouldn't be too bad. I expect you have a lot of them memorized already, okay? So just make sure that you've got that down for your test. As I said, I'm going to be grading you on notation. That's most important probably when we're talking about vectors. Now remember, vectors are quantities that have a direction and magnitude. Examples of vectors include position, velocity, acceleration, force, and a lot more. Now, this right here, R, is a position vector. Position vectors point from the origin to the position in question. All vectors are symbolized by putting an arrow over the top of them. That's our notation choice, okay? Now, this is the position vector R, and the components of R in the x, y, and z direction are 1.5, 2.7, and 9.3 meters, respectively, for x, y, and z. You could indicate this with either the bracket notation or the unit vector notation. Either are acceptable. Remember that vectors are indicated with these little wedge-shaped brackets here, the triangular brackets, in matter and interactions. So we're going to go with that. Or you can choose the unit vector notation, which would be 1.5 I hat plus 2.7 j hat plus 9.3 k hat, all in meters, okay? I hat, j hat, and k hat are the unit vectors in the x, y, and z directions, respectively. So they would be indicated 1, 0, 0, 0, 1, 0, or 0, 0, 1. All unit vectors, by the way, have length 1. All unit vectors are dimensionless, as these are, so you have to put the units somewhere else. Now, if you want to find the magnitude of a vector in 3 dimensions, you do the square root of the sum of the squares of its components. The magnitude, or length of a vector, is the scalar, and you indicate that you're taking the magnitude of a vector by putting absolute value signs around it. If you just write R equals with no arrow over the top, I'm going to assume that you mean the magnitude, by the way. All right? Now, you can find the unit vector associated with some arbitrary vector R, and that is found by taking the component in the x, y, and z directions, right, and dividing it by the magnitude. So the unit vector R hat is x over the magnitude of R, I hat, plus y over the magnitude of R, j hat, plus z over the magnitude of R, k hat. And as you can see here, this will give you a dimensionless vector because you're taking, for example, meters and dividing it by meters on the top and the bottom of each component. Once you've found a unit vector, you've also found the direction cosines. So any unit vector could be written as r hat is equal to cosine theta x I hat plus cosine theta y j hat plus cosine theta z k hat. And here the angles theta x, theta y, and theta z are the angles that the vector makes with the x, y, and z axes respectively. Okay, so those are your direction cosines, and they're shown here in this picture. We define some important vectors, the displacement, the velocity, and the acceleration, and the equations for those are shown on this slide. The displacement is the change in a position, so it's the final minus the initial position vector, where a vector's or an object's position has gone through some change in position in time. Remember, whenever you have a delta, it's always final minus initial. The average velocity is the displacement divided by the time interval that it took to go through that displacement. So V average here, the average velocity, is delta r over delta t. From this equation for the average velocity, we can find the position update equation, which says that the final position is equal to the initial position plus the average velocity times the time interval, t final minus t initial. Now, an average, of course, will go to a derivative if you shrink your delta t down. Okay, so if you take the limit of delta r over delta t as delta t approaches 0, then you end up with the time derivative of the position, which gives you your instantaneous velocity v equaling dr dt. Now, the average acceleration is the change in the velocity over the change in time. So it's a delta v over delta t. But yet again, if you take the limit as delta t goes to 0, you end up with the instantaneous acceleration. Acceleration is equal to dv dt. We also define the momentum of an object, p. P is equal to the mass times the velocity, mv. Remember, momentum is a vector, and SI units are derived here, kilograms meters per second. Forces are pushes or pulls. The SI unit of the force is the Newton. One of the first forces that we talked about was the gravitational force here on Earth. F is equal to mg, where m is the mass and g is the acceleration due to gravity here on planet Earth. That's 9.8 meters per second squared down. We went over Newton's laws. There's 3 of them. The first law is that unless acted upon by an outside or external force, objects in motion stay in motion and objects at rest stay at rest. This is also known as the law of inertia. Newton's second law says that for an object with mass m, the acceleration of that object will be equal to the sum of the forces acting on that object. Remember, force is a vector, so it's a vector sum. And then divided by the resistance to the change in motion, which is a mass. So the sum of the forces divided by the mass gives the acceleration, or F equals ma. F net equals ma, I guess I should say. We could write this in its differential form, which says that the net force acting on an object is equal to the time derivative of its momentum. So that's our second law. Newton's third law says that whenever one object exerts a force on a second object, the second object also exerts an equal force in the opposite direction on the first. This is often colloquially known as action-reaction. But mathematically, you could express it as F12 is equal to minus F21. A little bit more about mass. Mass is the inherent property of an object. It's independent of the object's surroundings, so something's mass would be the same here on Earth as it would be on Mars. Mass is independent of the method used to measure it. It's a scalar, and the SI unit of mass is the kilogram. Remember that mass isn't the same thing as weight, right? The weight is mg, right, where it's the mass times the acceleration due to gravity. We define the kinematics equations. Here I show the ones in 1D, but remember that they can be extrapolated to 3D, or at least these two right here can. We said that in one dimension, the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the displacement. So that was a 1D equation. It's really not too generalizable in this form. But you can write the this equation here in terms of the vector. So here, x final minus x initial is equal to v initial in the x times t plus 1/2 axt squared. You could write that as delta r, the displacement, is equal to the initial velocity vector times the time plus 1/2 times the acceleration vector times time squared. So that one would be easy to generalize to 3D. And also you could write v final is equal to v initial plus a times t, with the v's and the a's all as 3D vectors. Now, using these kinematics equations is a whole class of problems. Make sure that you can work them, okay? And remember that if there's so-called projectile motion problems, then for projectile motion, acceleration is equal to 0 for x motion, and the acceleration in the y direction is minus 9.8 meters per second squared down, okay? Remember that x and y in projectile motion are independent of one another, and we can make this assumption because we're ignoring air resistance, okay? Remember that the kinematics equations in general are only valid for constant acceleration situations. Now, we did cover a few forces which would not result in a constant acceleration, so be sure not to try and apply the kinematics equations to those situations. We talked about position versus time, velocity versus time, and acceleration versus time graphs. It's important to understand that these things are all related graphically, and that's because, of course, v is equal to dx dt and a is equal to dv dt, right? So that means that since a derivative is a slope, that you can extract from the slope of a graph what, for example, on a position versus time graph, you can extract what the velocity is. So the slope of a position versus time graph is the velocity graph, right? And the slope of the velocity graph is the acceleration graph. Now remember that for position versus time graphs, you're going to have a maximum in your position when it's a turning point, right? So for example, here at point B, the velocity is equal to 0 because the slope is a horizontal line at this point. If v is 0, then that means that even if it's just for a split second, it has to stop. And it does that, of course, when it's changing direction. When it's going from, say, traveling to the right to traveling to the left, then it's got to slow down and turn around. So you can figure out how to relate position, velocity, and acceleration graphs in the following way. The tangent line to the position versus time graph at the top of the curve there would be horizontal, so the slope is 0 there. That means the velocity is 0 at that point. And see, these graphs are related by the same time axis, so you can see that that's the case here. Now you can see that you've got an upwardly increasing curve there. That corresponds to a positive velocity, right? So the velocity is positive until the turning point where it goes to 0. Then the object starts to go down or starts to travel in the opposite direction. That corresponds to a negative velocity, and you can see that the slope is negative, and so is the velocity after the turning point. Remember that a negative velocity doesn't mean slow necessarily, okay? The magnitude gives you the speed. So a large magnitude of velocity is a high speed, whether it's negative or positive. Now on a velocity versus time graph, you can take the slope of that and get your acceleration. This is a straight line, which means that the acceleration is going to be constant, and it's negative, right? So it's a negative straight line, so that means that you're at the same constant acceleration. And of course, if this reminds you of projectile motion, it should. So, to sum up, here in the left-hand column is motion at constant velocity, and here in the right-hand column is motion at constant acceleration. These are two very common situations, right, for projectile motion. At constant velocity, this would be like your horizontal motion. You have an acceleration of 0. That corresponds to a constant velocity, right? It doesn't have to be a 0 constant, right? But it corresponds to a constant of some sort. But that does mean that your position is constantly changing. If you're moving, right, then your position will change. Okay, at constant acceleration, your acceleration is a straight horizontal line, right? But that results in a straight sloped line on your velocity versus time graph, which results in a parabolic curve on your position versus time graph. Moving on, we also talked about collisions and impulse. So during a collision, objects are going to be smushed a little bit due to the large forces involved. That's visualized here with this tennis ball hitting a racket. Now we know via Newton's second law that F is equal to the change in momentum divided by the change in time, okay? Now, if we take this equation and rearrange it, multiply both sides by delta t, then we've solved for the impulse. So the impulse is the force times the change in time, right? And that's equal to the change in momentum, which is equal to the impulse. The units of impulse are newtons times seconds. We also briefly covered spring forces. Here I've shown the value, or how we write it for a three-dimensional vector, to be as general as possible, okay? So, to review, remember that spring forces are dictated by Hooke's law. Hooke's law says that the force that a spring exerts on the object is going to be opposite to the displacement of that object from equilibrium, so that the force is always returning it to its unstretched or uncompressed spring length, right? And it's governed by K, the spring constant, which is basically how stiff the spring is, okay? Now, Hooke's law says that the force is equal to minus the spring constant times the displacement of the spring, or the mass on the spring, okay? Now, in 3D, we defined a vector L, which points from where the spring is attached to the mass, right? So here L, and then L naught is the length of the spring when it's relaxed. So then we can define the stretch of the spring S as the magnitude of L minus L naught. Then we write Hooke's law as F is equal to minus K times S times L hat, where L hat is the unit vector, of course, that points in the direction of L. We showed that if you solve F equals MA is equal to minus KX, that for a mass and a spring in 1D, then you get the position versus time graph that's sinusoidal. So that means that the position with respect to time, x of t, could be written as a cosine of omega t plus phi. Here, a is the amplitude of oscillation, which is the max displacement of that object from the equilibrium position in either direction. Omega is the angular frequency, which is equal to the square root of k over m, where k is the spring constant and m is the mass attached to the spring. Phi is the phase constant, which just tells you when you've started your clock, basically. Now, omega, the angular frequency, is equal to 2 pi times the regular frequency, f. F is the number of oscillations per second, and the SI unit of F is hertz. Omega is also equal to 2 pi over the period, big T. Remember that the period is the amount of time that it takes to go through one complete oscillation. We covered briefly Newton's law of universal gravitation. Newton found that any two bodies with mass are attracted to one another, and in its final form, the universal law of gravitation reads as follows. F is equal to minus g times the product of the masses, m1, m2, divided by the center-to-center distance between the masses, r squared. And then that points along the line connecting the two masses, center of mass to center of mass. So we find the unit vector r hat, okay, which points along that line. Remember that big G is the universal gravitational constant, 6.673 times 10 to the minus 11 Newton meters squared per kilogram squared. Remember that masses are always attracted to one another. That's why the minus sign is there in our F is equal to minus G, right? And so that means that it's going to point towards one another if this is M1 and M2. Remember that this is an action-reaction pair. So the force from 1 on 2 is minus the force from 2 on 1. They're equal in magnitude, but opposite in direction. We went through some steps as to how to calculate the gravitational force. This is the same kind of steps, by the way, that you would use to calculate the Coulomb force. So first, you're going to calculate that vector, that displacement vector, in between mass 1 and mass 2. And so that would just be by subtracting the two position vectors, r2 and r1. Next, you calculate the magnitude of that displacement vector, magnitude of r, and that's the distance between the two bodies center to center. Then you calculate the magnitude of the force, g m1 m2 over r squared. Then you calculate the unit vector associated with your displacement vector minus r hat. And then you just multiply your magnitude times that direction. Remember then that we solved for what the acceleration due to gravity little g here is on Earth by setting our weight equation mg equal to Newton's law of universal gravitation applied to planet Earth. So that would mean that for an object mass m, little m, here on Earth, little m times g would be equal to big G times little m times the mass of the Earth divided by the radius of the Earth squared. And if you cancel out the little m's in that equation, you can then solve for g and see that those numbers, g times the mass of the Earth divided by the radius of the Earth squared, actually give you 9.8 meters per second squared. What that means, though, is that if you're some distance above the Earth's surface, or, if you're at a point on the Earth where it deviates from the reported radius of Earth as shown in that equation, then your acceleration due to gravity can change. Remember that this is important when you're changing altitude, but it's also important if you're comparing, for example, the radius of the Earth at the poles to the radius of the Earth at the equator. Remember that the radius of the Earth at the equator is larger than to the poles. So you can calculate the change in little g. It doesn't vary too much over the surface of the Earth, maybe by 1% or so, but it's definitely something that could affect, for example, the period of a pendulum clock or something like that. Basically, it shows that little g decreases with increasing altitude, okay? And if you got infinitely far away from the center of the Earth, of course, your weight would go to 0. We then talked about the Coulomb Law force, and to do that we had to review the electric charges. Remember, there's two kinds of electric charges, positive and negative. Negative charges are the type possessed by electrons, and positive charges are the type possessed by protons. Neutrons, which also make up a lot of ordinary matter, have no net charge. Now, charges of the same sign repel one another, and charges with opposite signs attract one another. Charge is quantized, which means that even if you can't really tell for most everyday type charges, that it's going to be some number n times E, which is 1.6 times 10 to the minus 19 coulombs. That's the amount of charge that you would have on a proton or an electron. Now, since E is such a small number, sometimes it's hard to see this discretization, and so that's why it was only relatively recently, within the last 100 years or so, that we were able to talk about this. Okay? So the charge on a proton is plus 1.602 times 10 to the minus 19 coulombs, and the charge on an electron is minus 1.602 times 10 to the minus 19 coulombs. Here's Coulomb's law as written out. Remember that Coulomb's law gives the force in between two charges, Q1 and Q2. It's very similar in form to Newton's law of universal gravitation. In other words, you have some constant, right? And the constant times the product of the properties of the two objects divided by the inverse square of the distance in between those objects. They're both, in other words, inverse square law forces. Coulomb's law could be written as F is equal to 1 over 4 pi epsilon naught times Q1 times Q2 divided by the distance in between the two charges squared times r hat. Okay? Now, sometimes people like to talk about the Coulomb constant. Most of the time, I'll use epsilon naught because, let's face it, there's lots of k's in physics. And so I feel that epsilon naught is a little harder to get mixed up on. But 1 over 4 pi epsilon naught is often called the Coulomb constant. If you want to write it that way, that's a-okay with me. The Coulomb constant is 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. Epsilon naught is the permittivity of free space, which is 8.854 times 10 to the minus 12 in SI units. Remember that if you have multiple forces on any object, that the net force or the resultant force is going to be the sum of those forces. This is known as the superposition principle. So that's why we sometimes talk about F net or F average when we're talking about what's going on with Newton's second law on a force. This is going to become a lot more important in our next unit, however. So we talked about how the sum of the forces on an object is equal to the change in momentum divided by the change of time. That's Newton's second law, right? But if there's no external forces on a system, then that would mean that the sum of the forces, external forces, is equal to 0. And that would mean that the momentum delta P doesn't change in time, so delta P is equal to 0. So this is known as conservation of linear momentum, and is something that gets involved in a lot of collision problems where all of the forces are internal to the system. Now, it's important to understand that the momentum of the system is conserved, not necessarily the momentum of an individual particle. So a particle can change its velocity as long as, for example, the system has momentum conserved. Conservation of momentum can be expressed mathematically in a lot of different ways. Let's say that you just had two objects in your system, right? then you could say that the total momentum, which would be the sum of the momentum of object 1, P1 plus P2, that's a constant. So you could say that the total momentum has to be a constant, or you could say that the initial momentum has to be the final, equal to the final momentum. This is the form that I most often use, P initial equals P final, by the way. If you just had two objects, then that would be P1 initial plus P2 initial equals P1 final plus P2 final. But remember that if you had more than two objects, that you would just keep summing until you summed over all the objects in the system. Now remember that momentum is a vector. And so what that means is that you're going to have x, y, and z components for the momentum. And if that's the case, then the total momenta in each direction are independently conserved. So that's kind of nice to break it up and look at it component-wise sometimes. It makes the math a little easier to deal with. Okay, we're getting to the end. Finally, we talked about the center of mass of an object, which is a special point in a system that moves as if all of the mass of the system is concentrated at that point. Now, to find the center of mass of an object, or for a system of particles, you say that the center of mass R is equal to 1 over the total mass times the vector sum over all the objects of mi times ri, where ri is the position vector and mi is the mass of the ith object. Okay? So remember, this is a position vector, which points from the origin to the point in question. Okay? Now, if you take the time derivative of the center of mass position, then you find the velocity of the center of mass. So, expressing it that way, v center of mass is equal to dr center of mass dt. Now, breaking it out into the equation for the position of the center of mass, rcm, then you can see that what would happen mathematically is equal to the velocity of the center of mass would be the sum of the momenta of all the objects, P1 plus P2 plus P3, divided by the total mass of the system, big M, which would be the sum over all the masses, M1 plus M2 plus M3, and you keep going. So you could say that the momentum of the system, which I'll call P_sys, is equal to the total mass times the velocity of the center of mass. And sometimes that's a nice, easy way to find it. Okay, that sums up most of everything. Okay, I just hit the high points. Remember that you need to be able to work problems on all of these ideas. So, in my opinion, the best way to study for a physics test is to go in, make sure that you can work all the homework problems and understand what you did wrong when you were doing your homework if you got anything wrong. Make sure to work the practice tests that I post, and then also work extra problems, okay? So go through the end of chapter problems in chapters 1, 2, and 3, and pick what you think look like likely problems and make sure that you can do them, okay? Remember that the solutions to the odd number problems in matter and interactions are given in the back, and so you can work a question and then check your answer. Okay, I hope that helps, and I'll see you in class.